Welcome to the course Introduction to Algorithm. My name is Shoram Mukhopadhyay. I am a faculty member at IIT Kharagpur. I am lecturing this course. So this is lecture number 8 of this course. In this lecture we will cover the data structure hash function or hashing. So hashing is used for to store a set of records so that we can do the search in a faster way, and that set is a dynamic set where we should able to insert a record at any point of time, we should able to delete a record, and we should able to do the search in a faster way. So these three operations we want to do on this set, this dynamic set, and this operation we should do in a faster way. So we will talk about this data structure which can be used for this problem. This problem is called symbol table problem. So we have given a set of records or set of numbers, and we need to search a number in this set, that is the key, and then we need to insert a record whose key value is this, something like that. We need to delete a record whose key value is this. So we will talk about more on details regarding the key value. So this lecture will cover some construction of hash function, and then we will see the properties of hash function. We will see when a hash function is called a good hash function or bad hash function, and we will see what is called universal hashing in this lecture, and we will see also the perfect hashing, and so this so hash function, all about the hash function will be covered in this lecture. So let us start the lecture. So this is what is called symbol table problem. What is the problem? Problem is we have given some records. We have given n records, and each record is like this. This is one record. So for example, say student record. Each student have some field, roll number, name, CGPA, SGPA. So this is one student record, and among this field we choose one field to be key field depending on our application. Suppose we are more interested on CGPA of a student. We want to search the student based on the CGPA. So then we will put this CGPA field as a key field. So again, depending on the application, we can put the roll number as a key field. So that we can do we are looking for a student whose roll number is this, or so depending on the application, the key is decided among this field. So remaining field we can just ignore, but this is the part of this record. But we will do all type of operation based on this value of this key field. So we will store it, we will search it based on this value of this key field, but record is the whole thing. So when you store it, we should have in the memory we should store the whole thing, but only thing we will do the operations like searching, we can take care only taking this field. Okay. So now what type of operation we can think on? So this set is dynamic set. That means we should able to insert a new record, we should able to delete a record, and we should able this to makes this set makes this set dynamic, and we should able to search a record with key value something. So these four operations we should able to do on this set T. So we should able to insert a record, we should able to delete a record, and we should able to search a record whose key value is k. Okay. So this is the things. Now we need to think of a data structure for this set T, this dynamic set T. So now the first data structure in our mind may be array, another array. So given some given some key value, suppose we have some key value, say 6, 7, 2, 1, 20. This is our T at some point of time. So these are the key value corresponding to some record. So this is corresponding to some record X. This is corresponding to some record Y, this is corresponding to some record Z. So records are there in the memory, but only thing the operation we have to do based on the key value. So these are the key value. Now If we use a array, another array to store this record, so we just use a array to store this record. So we can just have a array of n numbers if there are n records. So then we store the records over here. So this array can store the key value to 1 like this, so 20, and we can keep some extra space in this array so that we can do this addition. We can do the insert operation there. So suppose you have to add a record whose value is 400. So we can go at the end of the array, we can insert that. So either we have to keep a track where the array is ending, or we can linearly search this array to get the null or empty or something like that. We need to take care while we implement. And delete, if we have to, suppose we want to delete 2. So we search it and then we delete it. And suppose we have to search a record. So this is an array of size n, say, then searching will be linear time. Okay, if it is unordered array, if it is not sorted. If it is sorted, we can do the binary search, but this is a unordered array, and this is deletion. Will, if we delete, we need to take care that this is deleted. So to avoid that, we can use linked list. So that is a dynamic version of this array implementation, and these are the key values of the record. So record is stored in some location in the memory. So maybe we can, to get the, because ultimately we need to get the record. So we can have some, here we can put some address over here to get the record. Okay, so that implementation issue we can take care by, suppose we provide the address of the record where it is stored. So we have to store this record in some portion of the memory, maybe main memory or RAM. So that address, virtual address, has to be stored here so that we can fetch the record. Because when we delete it, we should delete it from the memory, otherwise it will be a wastage of this. So that part we can take care whether we are implementing, but main thing we will be doing this operation based on the key value. So actual record is there in our database. Okay. So now the question is, array is taking order of n times, if it is unordered array, or linked list also order of n times. Now can you do something faster than that? The question is, can you do in linear time? That is more challenge. So for that we can think for another data structure which is basically an array, but this is called bit vector or direct access table. So what we do, we just if we know the values of these keys, if we know the where from this key will be coming, the maximum value. Suppose maximum value is say in the earlier example, maximum value is 20. So then we can have we can think for a array of size 20. So this is this k is coming from these values. Then we can have an array of that much size, say say this array is starting from 0 to say it is m minus 1. If we know the values are in between this. So we have, so then what is the data structure? These are the fields. We know if the record value, record key value will be fall in these numbers. So then we can just a bit vector. We will if 2 is there, so we will go to the 2, because in our previous example 2, 1, these are there. So 1 is there. So we can just go to this 1 position and we can put a 1. 2 is also there, we can put a 1. And then what are the other values? We have 1, 2, 7, 6, 7, 20. So we can go to the 1, 2, 6, 7. Sorry, this is say 6 is here roughly. So 6 is here, 7 is here roughly. Then 20 is here, say. I mean, if 20 is the maximum, then we can, if we are sure, then we can put this 20. So this is 0 to, so m is 21. So this is the way we can, if this is 20. Okay. So this is the data structure. So we use the tk. We use the tk is 1. So, we just have this value if this k is there. Otherwise, I mean, this is the just a bit vector, the record is present or absent, this will be 1. So, the record is there, otherwise it is 0. So, these are basically 0 1 representation, presence or absence, very good data structure, and this is what is called direct access table. So, depending on the values, the key values we have, we can have this. Now, this has a problem, and before the problem, let us think about what is the time for doing those operations, insert, delete. Suppose we want to insert say 3, so this is third position T3, so we can insert this record, that means we can insert a 1 over here. Inserting that record means the presence or absence, so we can insert a 1, that means this record is there, we can have an address here to where the actual record will be stored. So, that is the implementation issue. So, this is 3 if we have to insert 3. So, that is taking constant time because we are directly going to that position and we are storing that. Even delete also, we can go to that T of that, this is T3, we insert it. Suppose we want to delete T2, I mean the record 2, I mean the record whose key value is 2. So, we go to T2 and we know this was present, so we make it 0 and then we get the address and we can delete it from there. So, that is the way we do. So, this is linear time, and also search is also that. So, suppose we are searching a record whose key value is 3. So, we can or k, we can go to that position and we see whether this is 1 or 0, we get this address. So, this is just a linear, just a constant time, theta of 1, just we are going to that position and this. Now, the problem is, so very nice data structure, 0 1 bit representation, this is also called bit vector. Okay, the direct access table, this is also called, and this is also called bit vector. Now, what is the problem with this? Although this is very nice data structure, the problem is this. Suppose we know the record value is huge, value of a record, key value, say 2020. Then we have to keep that size of the array so big. So, for example, if we have a record with value this, so 64-bit number, so then we have to keep 2 to the power 64. If our each record is 64-bit, then what is the maximum value? Maximum value is 2 to the power 64. So, 2 to the power 64 is the array size, 2 to the power 64 minus 1, which is this much, which is very difficult. So, memory will be wastage, and moreover, suppose we are looking for say n records and our records size of the records is less, size of the key, say for example we are dealing with 100 keys and our key each key is 64-bit. So, then we are, although we are dealing with 100 keys which is small, and we need to keep this much array size. So, which is the, I mean really a sparse, I mean very much sparse and wasting of memory. So, that is the drawback of this type of direct access table or bit vector. So, to overcome this drawback, we will introduce what is called hash function, a new data structure. It's a function, it's a function from, this is a set of keys. Now, we fix the table size, we fix the records size, say we fix it from 0 to m minus 1. Suppose this is 64-bit keys, each key is a 64-bit, and suppose this is 8-bit. I mean we want to 8-bit, so that means this is 8-bit means so 2 to the power 8 minus 1, that will be the 0 to 2 to the power 8 minus 1 is the table size. So, this is the array size we want to store it. So, this is basically an array, but it is a fixed less size. So, it is basically depending on the how much we want to take this value of m. So, basically hash function is a function from set of u to this fixed size table slots. These are the table slots or array. So, any function from this is the universe of keys. We consider if key is 64-bit, this is the all possible 64-bit number So 2 to the power 64, this size, huge. And this is some fixed array, fixed size array. Okay. Now any mapping from U to this is called a hash function. Any mapping H, which is a function from U is the domain and this is the codomain. So that means if you take any key, it should map to a some slot over here, some array index over here. So that is the thing. So this is very less and this is very big. Now suppose we have such a function. Such function is called hash function. Any such function is called hash function. We will see some construction example of such hash function. So suppose we have such function h. H is a function which can take any key from here, from the universe of key or set of all possible keys, and which will map to a fixed slot over here. Which will go to the sum of the index of this array. This array size is 0 to n minus 1, which is very less than this size. Okay. So now suppose we consider our key, this T set, you can say. This is the dynamic set T, which is storing n records. Our possible keys is very big, but we are dealing with, at some point of time we are dealing with some n keys, which is less. Now how to do this, how to use this data structure, how to store this in this array? So what we do, we take a key k1 and we compute this hash function h of k1, it will hit to some of the slots. So suppose this is 0, 1, 2, suppose h of k1 is 2. So we store this k1 in array t2. So this is t0, t1, t2. So this is basically an array, or you can say this is a table. So we store this k1 here. Now we take another key k2 and suppose this is hitting here in this index, this is a ith index, so we store it here. We will keep on doing this. K3, it's storing, it's giving a value over here. So if you take any key, if we apply hash function on that h, it will give us one of the value. That is the definition of hash function. That is the way we take the hash function. So this K3 will be stored here. Now K4 will be stored here. So we are going very nicely. Now we will see a problem over here. Now suppose K5. So K5, when you compute, suppose it is hitting a slot which is not empty, which is already occupied by some key, and this situation is called collision. When a record to be inserted mapped to an already occupied slot in T, then it is called collision. So when we have a collision, we cannot store T1, K2, K5 in this. That is not allowed. So so one element will be in the one array positions over here. So that is the thing. So now the question is, collision we cannot avoid, because this h is a function from U to this. Now h cannot be a one-to-one function, because this set is huge, U, and this is smaller set. So from smaller set to larger set, so basically what h is a, just a minute. So h is a function from this set of all possible keys to this fixed slot 0, 1, this is the array indexing dot 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 m minus 1, sorry, m minus 1, which is less. So for this, so this size is very big. So this domain is very big, but this is smaller. So we cannot have a one-to-one mapping. So that means collision is expected. I mean, collision must be there. Only thing, this collision we need to tackle it. How to tackle it? So that we have to see. Collision we cannot avoid, because we cannot have a one-to-one mapping on this one-to-one mapping of H. That is not possible, because this is very big set, this is very small set. So domain is very, very big. Okay. So for that, how to handle the collision? So we will use the method of chaining. So whenever two or more keys will be colliding in some slot, we will have a linked list outside the table. So we will have a extra memory outside the table. So there it could be array also. Anyway, we use the linked list for make it dynamic. So this 49, 49, 86, 54 are mapped to same slot under that function, under that hash function h, which is I. So we have to have a chain outside the table. So this is the extra memory we should have. So now we want to see whether this chaining is good or bad. Now, okay, so chaining will be there if there is a collision, and collision will be there because we cannot have a one-to-one mapping. Now the question is, suppose, so we have a set of keys over here. So we have a set of keys over here, and we have universe of the key, and this we are mapping into this slot, okay, dot 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 dot. Now if this is say 100, this number k1, k2, k100, and this is say also 100. So we have 100 slot, we need to store 100 keys. So we are expected, but we don't know about the hash function. If the hash function is mapped all the 100 keys to a same slot, then we have a chain of size 100. So that is a bad hash function. So now the question is, when the hash function is called good hash function. So that means if the 100 keys will be distributed uniformly over this slot, that's all. So that is called a simple uniform hashing. So we want our hash function to be good in that sense that each key should be equally likely to be hashed to any one of these slots. So this uniformity will be there, so that not all the keys will be mapped to a same slot. So then we cannot, how small the k we take, the number of keys over here, then also we cannot have it. So hash function is a good hash function if it distribute the keys uniformly over this slot. See, if there are say 200 keys and if there are 100 slots, so obviously we cannot fill, we have to have chain. But in that case, if we follow the uniformity, then 100 keys will be distributed into 200 keys will be distributed into 100 slot. If it is uniform, then each slot will get 2 keys. So that is what is called load factor. So we define the load factor. If n is the number of keys and if m is the number of slot, we define the load factor to be n by m, and this is the expected or average number of keys per slot if our hash function is uniform hash function, that means good hash function. Otherwise, if a hash function is bad, that all keys are mapping to a same slot, then this has no meaning of this load factor. Okay, so we will see some example where we have a good hash function or bad hash function. Okay, so suppose we have a reasonably good hash function, and we have some keys and we have m slot to be these keys to be mapped. Then what is the search cost, or what is the insert cost? So how to search it or how to insert it? So we just do a hashing, and it will hit to some slot over there, and that slot is having a key having a chain of size alpha, that is the load factor. So we have to search that chain, basically search in the list, that linked list, that is a chaining that chain. So basically this is the cost. So we have to use a hash function, then we have to search in that list. So this will be order of n if that we have one slot is containing all the n keys, which is not uniform hash function. So then, which is a very bad, that is the worst case. In that case, this will be the this size is order of n, and we need to search in that list. So that is very bad. So that is the situation over here. Suppose this is the one slot is containing say all the keys. Okay, this is a linked list basically. Now suppose we are searching a key. This is the universe, this is the key, we are searching a key, say key something. So we will apply hash function. If it is hitting here, then we have a list of size n, so we need to linearly search. So that is the worst case. But the best case, if it is universal hashing, or sorry, if it is uniform hashing or good hash function, then this is the load factor. It will not be like this. So, it will be keys will be distributed uniformly over the slot, and if this is, if this load factor is linear, that means if alpha is order of n, order of 1, the constant. So, that is possible if n is equal to order of m, and that means if we have say 100 keys and if we have 50 slot, that is also, I mean, like that, n keys and m slot and 10 keys. So, the load factor will be 10. So, that is a constant. Okay. So, that is the depending on the this load factor. So, this if this is a this is this, and also if hash function is good hash function, simple uniform hashing, then we have this time complexity to be linear, constant time theta of 1 depending on this 2 factor. Okay. So, now we will construct some hash function. We have to, so this is the assumption, we need to choose the uniform, simple uniform hashing, which is hard to guarantee, but several common technique we will see. We will see some example where in practice we can achieve that. Okay. So, this is the good hash function. A good hash function should distribute the key uniformly into the slot of the table. So, that is what we are on. Regularity in the keys distribution should not affect the uniformity. So, keys we have, we do not know the keys. So, keys can be follow any distribution in keys. So, that should not affect in the distribution over the slot. So, that is called good hash function. So, now let us take some example of hash function, quickly we can go. So, suppose we have m slot, this is quite obvious example. Suppose our keys are integers of any length, big integers, that is the set of all universe of the keys, and then but we have a fixed table size n. So, now the question is, so we have some big integers as our keys, and we have fixed table size 0 to m minus 1, table size is m. So, it is 0 to m minus 1. Now, if you take an integer over here, some big integer 2 0 1 1 9 7, something like that, 5 6 5 9 6 1, some big integer, and suppose this m is say some fixed value, say this is if it is 2 to the power 4, then it is 16. So, this is 15 say. So, we have a table 0 to 15. So, everything so map to this. So, how to do that? The mod operation. So, we take a key, we take mod m, then mod operation will give us the remainder as 0 to m minus 1, because if it is more than m, again we can divide that. So, this is what is called division method of this division method. So, now the question is whether this hash function is a good hash function or bad hash function. So, it depends on the choice of this m. So, we will see if we choose m to be some 2 to the power something or 10 to the power something, then it is not a good hash function. Why? Let us consider this example. Suppose we choose m equal to 2 to the power r. Now, suppose r is 6. Now, we choose a m, we take an integer, we convert into binary. So, this is a binary representation of that integer. Now, what is h of k? What is mod k mod m? M is 2 to the power r, 2 to the power 6. So, that is basically last 6 numbers. So, that means this remaining most significant bits have no role in this value. So, if we change one of this, it will be hitting to same slot. So, there are huge number of collision will be there if we change one of this value. So, there how many bits are there? 2 to the power of that whole set will colliding to this if we just fix this last 6 bit. So, it is not a huge collision. We want this to be distributed over the slot. So, this is not a good choice of m if we want to use this modulus operation. So, good choice of m, we have people have observed that this is our h of k. So, good choice of m, people have observed that we should pick a m to be prime, which is not close to some power of 2 or power of 10. We don't know which number system we will take. Okay. So, but sometimes prime tables, this m is basically the table size, start from 0 to m minus 1. So, m is the table size, but sometimes the table size choosing prime is not convenient. Okay. So, now we will know another method where we can choose, because m is 2 to the power r is a quite reasonable choice, because say we have a we have a key size, say 64 bit. This is one key. So, k is 64 bit. Now, we want to make it into say 8 bit. Okay. So, that is hash function is basically compression function. So, you want to use a hash function which will take this key and which will be giving us 8 bit. So, 8 bit means what? 8 bit means what is the possible values? It is 0 to 2 to the power 8 minus 1. So, m is basically 2 to the power 8 here. So, in practice choice of m is 2 to the power some power is more common. So, that is why we want to learn a method of constructing hash function where we can choose m to be 2 to the power something. Okay, or say 10 to the power something, depending on the which number system we use. So, that is called multiplication method. Here we are allowed to choose m to be 2 to the power r. So, suppose our computer are w bit. So, now it is 64 bit. So, then what we do? We just take so our keys are also w bit. So, we choose a constant which is a w bit. So, we multiply key which is w bit and a. So, it is 2 w bit. Now, we want to make it again w bit. We take a 2 to the power w bit, and then we will take the right shift of w minus r bit. So, this will be basically this will give us the h of k. Okay, this is the bitwise right shift. So, we'll choose we'll see by an example. So, suppose m is 8. 2 to the power 3. So, whatever our size of the key we want to compress into 3 bit. So, m is 8. So, now our suppose key is 7 bit. So, we take a key over here. Now, this is our constant a, we choose a 7 bit. This is our w basically. Now, we multiply this operation, it will be a 2w bit, that means 14 bit. Now, we want to make it again 7 bit. So, we can do the 2 to the power this. So, this will be this part. Now, we want to do this right shift, because we want to make it 3 bit again. So, we want to do the right shift how many times? This is 7 minus 3 4 times. If we do right shift 4 times, this is gone, this is gone, this is gone, this is gone. So, this is our h of k. So, this is have a nice representation by the this modular wheel. Suppose this is the wheel. Now, this is a, we are multiplying by a. So, we are multiplying 1, twice, depending on the value of k, how many times we are multiplying, and eventually it will be come to some 3a. So, like this, sorry. So, eventually it will hit to some of the position over here. We cannot go beyond this wheel, because we are taking this ultimately this mod of this. So, this is a nice example where we can choose m to be 2 to the power r. Now, we can take another example. This is what is called randomized strategy. This we will see more details when we talk about the universal hashing. So, here what we do? We take m to be prime number here, and then we have a key. We divide the key into some blocks, and each block is a less than equal to m. So, this block, this is one block, first block, second block, and each block value is less than m. And we choose a which is randomly we will choose, and then each of ai is coming again from this. So, then we have a dot product on this to get the hash function of k, and this it is also a function of a. So if we choose another A, it will give us another Hash function. So this will discuss in more details when we talk about collection of hash function, when it is called universal hash function, that will be coming soon. Okay, so now let us go to the another topic, which is called open addressing. Now open addressing means, so far we have seen to handle the collision, what we did, we had a chaining method outside the table. So we had a linked list outside the table. So that means we have a extra memory we are thinking. We have given an array, the table. Other than that, we have extra memory. So suppose this is not allowed. Suppose there is no storage is allowed, no storage is used outside the table or hash array is or the given array is given. So everything we have to manage there. So that is the challenge. Whatever the table is given or whatever the array is given, this is the 0 to m minus 1, whatever the array is given, everything we have to manage there. We are not allowed to have any chain or any extra memory outside the table. So chaining is not possible over here. Then how we can handle that, how we can handle the collision. And moreover here we need to assume that the number of keys should be less than number of slots, because otherwise if number of slot is less and number of keys more, then we cannot fit into this given array. So here we have to assume that number of keys, that n is less than m number of slots, so that we can manage everything in that given table. No need to go for the extra storage or extra memory in that chain. So what we do, we just use a family of hash function. This is sort of family of hash function, and these are called probe sequence. So probe numbers. So each probe number will give us a different hash function. So we will use the hash function, given a key we will use hash function, it will hit to some slot. If the slot is not empty, if the slot is occupied, then we have to try for next slot. So how we can try that? We have to again apply another hash function, because if we use the same hash function, it will hit to the same slot which is occupied. So we use another hash function, so that may hit to different slot. So this is a family of hash functions. So now the hash function is a function u cross, this is the probe sequence or the sequence of different hash function to this fixed slot. So this is the u of k0 is the first hash function, say this one. Okay. Now if it is hitting to some occupied slot, then we have to go for second hash function. So second probe. So we have a sequence of probes. This is the second attempt or 1th attempt, this is 0th attempt. So this is, you can say, h1 of k, this is h0 of k, the original hash function. Like this we continue, and this sequence should be a permutation of this sequence, because it should hit to different slots over here. So this should be a permutation of this sequence. Okay. Now we will see the deletion may not be straightforward, it needs some trick there, but it is not impossible, we will see that. So first let us take some example of this. Okay, so let us take an example of open addressing. So here what we are doing, suppose we have some, this is the current table, we have some keys already inserted there. Now suppose we want to insert a new record with whose key value is 496, and these are the already inserted record we have in the table. So now we have to insert 496. So what we do? We first choose the first attempt or the 0th probe. So that is the, you can say H0. I mean, this is first hash function, you can say. If we consider this as we have a family of hash function. So this is H0 of 496. Suppose it is hitting to a occupied slot. So then we have a collision. So once we have a collision, then we have to go for the next probe. So next attempt. So then we have to choose, we have to follow the next probe. So that is H1 of 496. So suppose this is also hitting to a occupied slot. So we have a collision. So again we have to go for the next probe. So this is the probe sequence, and this will continue until we reach to a, until we get a, until it will hit to a empty slot. Once it will hit to a empty slot, we will insert that key, or we will insert that record into that slot. Okay. So now, so this is collision, we have to go for the next proof. That means this is H1 of this is another hash, family of hash function we have say. So then we have to calculate, we have to go for the next proof, or H2 of that, another hash function say. So how we will do, we will take some example. Now we got a empty slot and we will insert that record into that slot. So this is the key value of that record we inserted in this in this empty slot. So this is the thing. So we have to follow this probe sequence when we, so this is the probe sequence, and when we search the key, the same probe sequence will give us the key, but we don't know, we don't store the probe sequence. It is not possible to store the probe sequence. So we have to start from the first H0, H1, H2 like this until we get a, so searching we will do now. So the searching will be, suppose we are searching 496. So how to search? So search will be, search use the same probe sequence, and it will terminate successfully. I mean, every time we will check whether we are getting that key is same as with what we are searching, or if we have, if we reach to a empty slot, then we stop, because if we reach to a empty slot, then there is no question of searching further. So that is the strategy we use. But only thing, we don't know the probe sequence, so we have to start from the 0th probe, 1 probe like this. So H0, H1 like this. So let us start searching this key, searching the record whose key value is this. So we do the 0th probe, H0 of that, it will hit to this slot which is a which is 204, but we are searching 496. We will check that it is not 496, then we have to go for the next probe. So next probe it is hitting this, which is 586, which is not 496. We have to go for the next probe. So this will continue until we reach to, until we get the number, get the record whose key value is this, or we reach to a empty slot. Then we reach to here, and then we compare this value with this, and it is matching, we got the record, Eureka. So this is the same probe sequence we had to follow to get the record. Now, now for deletion, why it is empty, why it is difficult? Because suppose in this scenario, suppose we will be searching this once it is inserted, and suppose we are deleting, say we are deleting this 586, we are deleting the record whose key value is this. Now after deletion, we are searching the 496, which already there. So if you do that, it will for 0th probe it will hit here, we will check whether this is same or not. It is not same, we have to go for the next probe, but next probe it will hit to empty slot. So it is misleading us. So our strategy is telling we should stop, but this is not originally empty. It got somebody was there, some record was there which got deleted. So to keep track of that, we can use some field over here in this table to indicate that the somebody was there. So when we reach to a, when the searching, when we reach to a empty slot, we have to check that field, because if we are allowing the deletion in that way, we have to check that field. Okay, it is empty, then we check this field, oh no, it was, somebody was there, got deleted, so we have to go further. So then we have to go for the further probing for searching 496. So that is the deletion can be handled in that way. Okay, so now we will take some example of this probing. First one is linear probing. It is, the idea is basically when we hit to a slot, so we just check the whether the next slot is available or not. So suppose it is hitting this slot, some key when inserting, suppose it is hitting this slot. Now we will check whether if it is not empty, if it is occupied, collision, then we will check next slot. If again that is empty, next slot. That is the idea. So this is the functional form, this is the probe sequence. So the 0th probe is the suppose this is the original hash function. We have choose a ordinary hash function which is h prime k. So we apply that hash function and it will hit to some slot. If there is a collision, then we have to go for the 1, I is equal to 1, and that is basically the wherever it is hitting plus 1, that means the next slot. And then again if it is collision, even if this is not empty, we have to go for the next probe. So linearly we are doing, and we take mod m because after if it is coming here we have to come back here. So this is everything we have to take in mod m. So this has a problem, this method. Problem is it will cluster. If some slot it is hitting, then it will make a cluster over that slot. So it is a cluster basically. It is not uniform distribution of the keys over the slot. So this hashing is, this linear probing is not a good hashing in that sense. Okay, so to do the something good in uniform hashing, you can say we use two hash function, we choose two hash function, two ordinary hash function h1, h2. Then in the 0th probe we will use only h1 if it is hitting some slot which is collision. Then in the next probe we will calculate h2, then we will add it up, then take the mod, and then we will check whether that is available or not. If not, then already we have calculated h1, h2, then we compute this h1k plus 2h2k, then obviously we need to take mod, and then it will hit to some slot. If it is still collision, then again we have to go for 3 like this. So this is better than the linear probing, and in practice we have seen this is, even we can have more than this, like I squared, some k3 we can choose h3k, another hash function. So like this. So this is a good hash function in that sense. We people have observed this. Okay. So so this is one observation. Now let us analyze this open addressing, whether this is good or not. So we will see that if our hash function is if we assume the uniform hashing, then it is a good hash function. So that is if each key is equally likely to be any one of this, that means each key is equally likely to be any one of these slots. So these permutations are equally likely. So then we can show this is a good idea of doing the handling the collision. So this is the theorem, we are going to prove it. Given an open address hash table with a load factor alpha, so it is a uniform distribution n by m. So obviously n is, because in the open addressing n has to be less than m, because everything we need to do in a same table, we have no extra storage outside the table, so no chaining is allowed. So obviously say n is say if n is 100, and if we have table size 50, we cannot do it. So we must have at least 100 or 200 table size. So n must be less than m. So that means alpha is less than 1 always. So this is the assumption for open addressing. So now this expected runtime, expected number of probes for unsuccessful search is this. So what do you mean the unsuccessful search? We are searching a key which is not in the table, which is not in the record. So that is called unsuccessful, and that time is for that we need to do this number of probes. So how to prove that? So to prove that we will use the this probability theory. So now if we are searching a key which is not there, then one first probe is required. So that is necessary, and when you will go for next probe, if that is hitting to a occupied slot. So suppose we have a this is the table, this is the table, and there are m slot, and suppose there are n keys already there, n keys are already there. So k1, k2, kn in some way there. Now we are searching a key which is not there, so we search a key, it will hit to some slot. Now when we will go for the next probe, if it is collision, so what is the probability of collision? There are m slot and n keys, so collision will be n by n, just a classical probability. Then only you will go for the next probe, and then when you go for next probe, if again collision, and that will be n minus 1 by m minus 1. So this way we will continue, and we will use this result, this n minus. So that is in the next slide we will see. So this is the thing. So first probe is mandatory, then when we will go for the next probe with this probability, and then next to next probe with this probability. This is the probability of collision. So this way we go. Now these are all less than in m by m. So these are all basically less than equal to alpha. Now we take this, and this is less than equal to infinite series, and this is basically power series 1 by 1 minus alpha, because alpha is less than 1. Now if alpha is, say if our table is half full, if alpha is half, that is 0.5, then it is basically 1 by 1 minus alpha is 2. That means basically if our table is half full, then we need to do the 2 probe to have a unsuccessful search, which is quite reasonable. But if the table is quite full, like 90%, then it is 1 by 1 minus alpha is 10. So that means 10 probe is required. Okay, so next topic is we will discuss is what is called universal hashing. So for that we need to discuss this weakness of hash function. Okay, so let us talk about fundamental weakness of hash function. Given any hash function, it is a function from a universe of key to a fixed size slot. So the domain is very big and codomain is small, so we cannot have a bijective mapping. So given any hash function, if we have time, we can get such a set where all will collide to a fixed slot, I mean J. So that we can do if we can try for all possible keys like this, then we can construct such a hash function. So this is a fundamental weakness of any hash function. So if we construct a hash function, so if we submit for a approval, then the adversary can try for some possible keys and can come with this set easily, so that it will basically if we have time we can try for. So that is possible. We can always get some group of keys which will map to the fixed slot, and that is collision is very obvious. Okay, only thing we need to search the keys there. Okay, so that is the fundamental weakness of hash function. To avoid that, what we can do, we can choose, if we have a collection of hash function, if we choose the hash function randomly at the runtime, then our adversary cannot come with the such a, because adversary will not be knowing which hash function will be selected at the runtime. So it is similar to randomized version of the quicksort, randomized pivot, random pivot. Okay, similar idea. So so that is the choice of the hash function is random, and even if an adversary can see your code, he or she cannot find the bad set of key. This is the bad set of key, bad portion of bad set of keys, since he or she does not know exactly which hash function going to be chosen. So that will be decided at the runtime, execution time. So that is the advantage. So we are looking for some group of hash function or some collection of hash function. From there we can choose a hash function at random. So now let us talk about a good collection of hash function, that is called universal hashing. So let us consider a collection of hash function, which is a function, all hash function from U to this set, and this collection will be called universal collection. If this set is basically, if we choose a hash function from this portion, this is the whole portion, and this is the cardinality of whole portion. If we choose a hash function from this portion, then for any two key xy they will collide. For any two key xy they will collide. So this portion, all the functions are bad function. So they will give the collision. So now, and if this size of this bad portion is 1 by m fraction of the total size, then this collection is called universal collection, and we will see it is a good collection. So now if we choose a hash function from this universal collection, now then given any two key, what is the chance they will collide? Now they will collide if this hash function, randomly chosen hash function is coming from this set. So what is the probability of that? Size of this by total size. So that is 1 by m. So 1 by m is the probability of that. So now that will give us this thing that if we choose a hash function randomly from this collection, universal collection, then the expected number of collision with any key is less than m by n, that is the load factor. So that is good. So that hashing is very good. So because the expected number of collision with a key is less than n by m, where n is the number of keys stored in the table and m is the number of slot. So, given any key, if this is the thing, then we are done. So, this proof we are not discussing here. Now, let us take an example of a universal hash function, construction of universal hash function. So, suppose our key is say suppose we break the key into we will come back to those. So, we break the key into R 0 to R, so R plus 1 blocks, and each blocks is the value up to m. So, each blocks is value 0 to m minus 1. So, we can break the key, this is a long key, we block into divide into this many. Now, we choose a vector, random vector, and this each entries of this vector are chosen randomly from this. So, it could be any value from this. Now, if you vary a, it will give us different hash function. Now, how to define the hash function? We fix a, that means we fix these ai's. So, h of ai is the basically the dot product of this vector and this vector, which is basically this, and the table size is n, we need to take the mod. So, that is what we are doing here. So, this is the dot product of this. So, we have, so how many such functions are there? So, it is basically the choice of a's. So, each of ai can m ways. So, there are total r plus 1. So, this is m to the power r plus 1, that is the size cardinality of this collection of hash function. So, now why this is a universal hashing? This is universal hashing because we can prove this cardinality of the bad portion is 1 by m fraction of the total. So, for that we can take two distinct key, and for that we can choose x0 and y0 is not same, and then we suppose their hash value is equal. So, from there we can just prove that how many times they will collide. We can get the A1 to be this. So, we have a choice for A2, A3 up to A1, A2, AR. We do not have a choice for A0. So, the size of this set is basically, so m to the power r into 1. So, m to the power r means we have a choice for these all, but A0 is fixed in that case. So, which is basically 1 by m fraction of the total portion. So, this collection is a good collection. We can choose a hash function from there. So, the last topic is what is called perfect hashing. So, perfect hashing means it is a static arrangement. So, we have given n keys and we need to construct a table, hash table of size n, m is equal to size n, so that search will take constant time in worst case. So, it is basically the two level hashing. So, we choose a good hash function in the first level. So, we have n keys. So, we distribute over the slots, we have same slot. Now, there will be some collision. So, if it is a good hash function, it will be uniform sort of. So, if there are collision, if there are one slot is having more keys, say ni keys, then we will go for the next level hash function, another hash function, and in that second level, we will use the table size square of the size of the keys which is colliding here. So, we will take an example. Suppose this is the situation, we have the first level, these are the keys. So, first level, this keys 14 and 27 is hashed to this slot. So, h of 14 equal to h of 27, which is 1. So, then they are colliding, and this is, we can get it this picture statically because we know the keys, we can put it into the slot, then we know how many are the collision is occurring, what is there is no collision in this level, in this slot. So, there are two keys are colliding here. So, we need to choose a second level hash table of size 2 square 4, and in second level we have to use another hash function. So, that hash function we can choose a, that a you remember that just now we have seen. So, that a will give us the hash function. So, h of 31 of 14 is, this is 0, 1, 2, 3. So, 1 and this is going to 2, that is it. So, similarly these are the keys which are colliding to 6 in the first level. So, there are 3. So, we have to take a hash table of for the second level 9. So, the square of that to be ensure that there will be no collision in the second level. That is why if ni is the number of keys colliding in the ith slot, we are choosing the table size for the second level is ni square. So, that is the guarantee, that is sort of the at the second level we do not want any collision. So, this is the 2 level hashing basically, and how to search it. So, suppose we are searching 37, what to do? We first apply the first level hash function, it will hit to 6 slot, and we know there is another level hash function. Then where to get the hash function? This 86, h of 86 will give us the hash function. So, here we have to store the second level hash function. So, this is the easier way to do that. This is our A basically. So, summation of ai ki. So, that will if we apply second level hashing, it will hit here, we compare, we got the value. Okay. So, this is very nice data structure, 2 level hashing, this is called perfect. Let us quickly analyze that, because we are taking the n square in the second level for this is basically ni square, for ni is key, there will be no collision. So, this we can prove by this theorem. This theorem is telling that if n is the key, the expected number of collision is less than half. I mean, we cannot expect half collision. So, since this is a universal collection is universal, we are choosing hash function from, so universal collection. So, 2 keys will be collide with probability 1 by n. Now, hash table is 1 by n square, there are n keys. So, n is basically ni here. Now, what is the number of pair of keys? NC2. So, what is the expected number of collision? NC2 into 1 by n square, which is less than half. Okay. Now, we have to think for the, so second level there will be no collision, and this is the probability of no collision. In the probability of no collision is less than half, even we cannot expect one collision. So, that is can be proved by this Markov inequality, which is you can see here. Now, we have to discuss the storage complexity, because we are taking square of the ni square as the second level storage. So, intuitively we may thinking that we are taking huge storage, no. So, that we can analyze. So, the total storage is, so at the first level we are taking m is order of n, and that is m plus summation of ni square, and this expected value we can show order of n. So, total is order of n. So, this proof is same as bucket sort time complexity. A bucket sort, there we have used this proof to show that if ni's are colliding in the ith bucket, then the summation of ni square is order of n. So, this time is also order of n. Okay. So, now let us conclude the lecture. In this lecture we have discussed hash function, which is a data structure to solve to store some records, so that we can search in a very nicely constant time. Thank you.